Title: Photogrammetry for Digital Twinning Industry 4.0 Systems. Abstract: The paper explores the use of photogrammetry and 3D scanning techniques to create accurate visual representations of physical processes for digital twinning in Industry 4.0 systems. By leveraging a consumer-grade device with stereo vision capabilities, the authors capture depth images of an Industry 4.0 system and process these images using 3D scanning tools to create a raw 3D model. This model is then refined in 3D modeling and rendering software for the creation of a digital twin model. The reliability of this method is demonstrated by measuring the error rate between ground truth measurements and the final 3D model, showing an overall mean error of 4.97% and a standard deviation error of 5.54%. The results indicate that photogrammetry using consumer-grade devices can be an efficient and cost-effective approach to creating digital twins for smart manufacturing, with the flexibility to allow for iterative improvements of the models over time. Introduction. The onset of Industry 4.0 is transforming the manufacturing world through the integration of cloud computing, machine learning, artificial intelligence, and universal network connectivity, resulting in performance optimization and increased productivity. Digital twins are one such transformational technology that leverages software systems to replicate physical process behavior, representing the physical process in a digital environment. This paper aims to explore the use of photogrammetry and 3D scanning techniques to create accurate visual representations of the physical process, to interact with the ML, AI-based behavior models. Literature review. The related work is divided into two subsections: digital twin and photogrammetry. A DT aims to establish a mirrored connection between the physical and virtual realms, mapping sensor-measured data onto the virtual model. Photogrammetry is the measurement of an object's distances from multiple photographs of the same object, which can be used to generate accurate 3D models of physical objects through stereovision photogrammetry. Methodology. The methodology aims to leverage photogrammetry to obtain 3D models to integrate with the DT4I4 framework. The process involves multiple stages: camera calibration stage, image pair rectification stage, and spacepoint coordinate calculation stage. This section describes each of these stages. Experimental evaluation and results. The paper highlights procedural considerations and error rates in results between the ground truth measurements and photogrammetry model. The results from this work indicate that photogrammetry using consumer-grade devices can be an efficient and cost-efficient approach to creating DTs for smart manufacturing, while the approach's flexibility allows for iterative improvements of the models over time. Conclusion. The paper concludes that photogrammetry using consumer-grade devices can be an efficient and cost-efficient approach to creating DTs for smart manufacturing, with the flexibility to allow for iterative improvements of the models over time. The results indicate that photogrammetry using consumer-grade devices can be an efficient and cost-efficient approach to creating DTs for smart manufacturing, while the approach's flexibility allows for iterative improvements of the models over time. Camera calibration is a critical step in the process of 3D modeling, as it extracts metric information from 2D images to estimate a camera's intrinsic and extrinsic parameters. These parameters are essential for interpreting each sensor pixel as a ray cast into the scene, providing crucial directional information about captured objects. The calibration process involves capturing images of a known geometry, allowing for the extraction of a rigid transformation to convert 3D world coordinates into the camera's 3D coordinates. This process is shown in Figure 2 and enables accurate camera calibration, which is crucial for accurate reconstruction of the scene's geometry. The intrinsic and extrinsic parameters are configured using a planar pattern-based camera calibration algorithm. This algorithm establishes the relationship between 3D points and their 2D projections, as explained by equations 1 and 2. The relative position of both stereo cameras is determined by calculating the associated external parameters, as shown in equation 3. This information is then used to align points in the left and right images on the same plane, a process known as image pair rectification, which is described by equation 4. Once the images are rectified, the coordinates of points in space can be determined using the triangle measuring method, as defined by equation 5. This method utilizes the pixel focal length of the left camera, the optical center distance between both cameras, and the principal point coordinate of the left camera to calculate the spatial point cloud. The spatial point cloud represents the 3D shape of the object and can be fit to obtain a curved surface, completing the 3D reconstruction process. The experimental setup for this study was conducted at the U-Arizona Future Factory, which is an Industry 4.0 system comprising of 4 SMC's Smart Innovation Factory, SIF, 400 stations. The SIF 400 simulates an automated smart factory that utilizes Industry 4.0 technologies, leveraging manufacturing concepts and the connectivity of real-world factories in areas such as production, assembly, logistics, and management. The system is connected machine to machine using management software that allows for the process to be fully automated. Figures 3 and 4 showcase the labeled snapshots and reconstructed 3D models of the front and top sections of the object, respectively, demonstrating the effectiveness of the proposed method in accurately modeling complex objects. The research paper discusses the creation of a visual digital twin for the SIF 405 capping station using photogrammetry and lidar scanning. The process involves 4 steps: obtaining ground truth measurements, acquiring images using stereovision cameras, processing images with Polycam, and digitally processing the output with Blender. The authors focus on evaluating the methodology for building 3D models of the capping station. They present experiments on measuring the accuracy of the front section, comparing scanned data with baseline measurements. The results demonstrate the effectiveness of the photogrammetry and lidar scanning approach in creating accurate 3D models. The paper highlights the importance of software tools like Polycam and Blender in enhancing the accuracy and usability of the 3D models. The paper presents a methodology for creating visualizations for smart manufacturing digital twins using consumer-grade hardware and software. The authors conducted 3 experiments to measure the accuracy of the digital twin's physical dimensions. In Experiment 1, they compared the measured dimensions from scanned reconstructions to actual measurements, finding error rates between 1020% for small details and 510% for most dimensions. In Experiment 2, they recorded the length, width, and height of major components from a side view, observing error rates of 16% for most dimensions, with higher rates for certain measurements. In Experiment 3, they recorded actual measurements of major components from a top view, finding error rates under 8% for most parts, with some higher errors in the width direction. The authors highlight the importance of accurately reflecting physical systems in virtual spaces for digital twins, which can enable the replication of physical processes in a cyber-physical system. They note that factors such as subject location, background complexity, and environmental conditions can affect the accuracy of the digital twin. Despite these limitations, the method produced roughly 9,095% accurate dimensions. The paper also provides an extensive list of references, citing various studies on digital twins, photogrammetry, and stereovision. These references support the author's methodology and provide context for the importance of accurate digital representations of physical systems. Overall, the authors demonstrate the feasibility of using consumer-grade hardware and software to create accurate digital twins for smart manufacturing, highlighting the potential benefits of this technology for Industry 4.0 systems.